One of the first tasks in an elementary statistics course is learning to compute measures of central tendency, and that is mean, median, mode, also measures of dispersion, standard deviation, variance, range, and so on. Two procedures that allow us to compute these summary statistics are the univariate procedure and the means procedure. When we have a SAS data set defined, we can operate on that data set, any of the numeric variables in that data set, using either of these two procedures. So in this first Chapter 3 video, we'll talk about the univariate procedure. The basic syntax for the univariate procedure we see on screen here. We need a proc univariate statement where we identify the data set. There are some options then we can select for this univariate procedure. We now know what a by statement is, and so that's going to require some sorting be done to our data. We know those variables can be sorted in either ascending or descending order. And then we have a VAR statement. Which variables do you wish to have summary statistics computed for? And then a histogram statement. So we want the univariate procedure to draw histograms for us. So we'll go through the three objectives on the univariate procedure. The last one, I believe, is that how to output some of these summary statistics to a new SAS data set, and we create a data set within a procedure. So this is a little new for us. It'll be a data set created outside of a data step. In Chapter 3, we introduce a new data set called instruction. And so very briefly here, that we have two instructional programs that are to be compared. Students are independently participating in one of the two programs. Scores at the completion of an instructional period are recorded for each of the students, and the data are given in this table here for programs A and B. In Objective 3.1, we need to create the SAS dataset instruction in the SAS editor with the character variable program and the numeric variable score. We'll look at the default information produced by the univariate procedure for the numeric score variable. So it doesn't matter here in the input statement if we define program first or second, but so long as we identify it as character, that is following here with a space and a $ for program. And so we've also used the double trailing at for the input statement, and so what this means is it's going to allow SAS to read across the page. So it's going to be A71 for program and score, program A score 82, program A score 88. So what might look a little repetitive here is that we're repeating A all the way across here, and this is because we've said you're identifying two pieces of information each time, and so that's why we need that repetition, so we make sure we understand how SAS is reading things in after this data line statement. If we forget to put the double trailing at here and simply had input program $score, then semicolon, then it would read A71, A81, B65, B90, and B73. It would only pick up those 5 observations instead of all of these that are written over here to the right. So we want to make sure that we use the at here if we're going to allow the data to be written with more than one observation per line in the program. So in this SAS editor, we have the creation of the SAS dataset instruction using the data step with the 3 commands data, input, data lines. Notice we have a semicolon on a line by itself after the data. All of our data are kind of this backlit or highlighted in yellow. And then we have the proc univariate statement occurring after the data are created, and we say which data set it's operating on. Now then, in the statement of the objective in the book, it says to examine the default information produced by the univariate procedure for the score variable. So what that means then is that I don't have any modifications on the proc univariate statement. There are no options selected, and so that's what we mean by default. And so I just proc univariate and score and see what the default information that we get out of this is going to be. And so once we have this, then we can run our program. we look at the log. We have the creation of the SAS dataset instruction, input data lines. We can see that it's telling me it reached past the end of a line. That's because of that double trailing at. We have 30 observations and two variables for certain. We didn't count our data, but there are 30 observations, I believe, in the programs A and B combined. We want to look at what univariate's going to compute for us for the score variable, and then those results occur in the results viewer. Now whenever you see the results window here to the left, again this corresponds to like a table of contents for your output, and so you can expand on each of these, and so it's generating several tables represented by each one of these. And so moments is the first. This is also the first page if we would have gone directly to results viewer and clicked there. It tells me what the default information is. And so we have this first table of moments, which has information about n or sample size. We have the mean, standard deviation. Some of these we know automatically what those are, so we recognize a few things then from a statistics class. And we have a few skewness and kurtosis. Those may be new to you. Basic statistical measures. So we notice the title of this table is also one of these things over here. It repeats the measures of central tendency here, which were our mean. We didn't have median or mode printed above. So variability, standard deviation, and variance. We saw those two up here. Range is computed as the highest score minus the lowest, and then our interquartile range, or IQR. We haven't talked about quartiles yet. It does a test for whether mu0 equals 0. We'll talk about this in just a little bit. Our quantiles, and so it's got our maximum score, 99th percentile, 95th percentile, so forth, all the way down to our minimum score. The middle range value, the 50th percentile, is the median, and if we look, that matches what we have up above here for median is 81. Our high score was 92. Our low score was 59. I don't need to use a sort procedure. It automatically put those things in order for me. Extreme observations, by default, it's going to generate what the 5 lowest observations are and what the 5 highest observations are. So why would I want to know that? Sometimes the typographical errors that you can make are missing a digit or typing a digit too many times, and so you can have in here, if you would have said instead of 59, if you would have left off and just put that as 5, your lowest value observation would have been a 5. That would be evident here. You'd see it here as well. Similarly, if you put in say 992, you would end up with a maximum score that looks very different from the rest of your data. So one of the reasons we look at these extreme observations is a matter of data checking, making sure we haven't made any typographical errors when we enter the data. And that's all of the tables that it prepared for me. Now, if we revisit this test for location, what is going on here? It's looking at a hypothesis test. It's computing 3 different test statistics, and we'll talk about one of those just now. So let's revisit the notes. When we revisit the book, it gives us some information on hypothesis testing, so notation for population parameters and the sample statistics that are computed that estimate those parameters. And so in table 3.1, we can see for a 2-sided test for the mean, where we conduct a t-test, we have a 2-sided rejection region, and how we compute the confidence interval. So what's going on in the univariate procedure is it's testing whether or not this mean is equal to 0. And it computes the t-test for doing that, and it computes a p-value for that application. We can also request confidence intervals, and that as one of our options. So when I move back to SAS and I look at this test for location, the student's t 49.33, etc., p-value less than 1/10,000th, that first row of this table under the headings, and that corresponds to that t-test in table 3.1. You may recall also there are one-sided alternative hypotheses for a t-test, and those aren't available here. We only written that in terms of the one-sided test, and so it's testing whether or not the mean of the population being represented by these scores is equal to 0, and this p-value is very extreme, and so therefore we would conclude that the mean is definitely different than 0. So the default setting here is 0, and so what we may want to look at is, well, what if we want to look at the mean being something different? And so we see this 79.66. Our data is nowhere near 0. We don't have any observation near 0. Recall the lowest one was 59. In Table 3.2, there is a review of the hypothesis test for a variance. So when we have a 0 subscript here, that means we assign the value here. It's a chi-square test, and of importance to us is this confidence interval for a variance of the population, and so that it's dependent upon the sample variances here. Additionally, Chapter 3 discussed this test for normality, where the normal distribution is what is assumed in the null hypothesis, and that the data are not normally distributed is what is represented in the alternative hypothesis. Most introductory statistics courses don't go through this test, but we also know that many of our methods require that our data are normally distributed. So without giving you all the possible test statistics for evaluating whether or not the data in the sample come from a population that is normally distributed, we're just going to summarize this briefly. So these are the hypotheses being tested. You're going to find multiple tests in your output and the references given here, and so that if we see a p-value associated with these test statistics for normality, if that p-value is small, that is evident that the data are not normally distributed, and if the p-value is large, that supports the null hypothesis that the data comes from a normal distribution. And so we'll look at that in Objective 3.2. In Objective 3.2, we're asked to use a class statement and score as the analysis variable to compute the summary statistics, the 99% confidence intervals, and a test for normality for each program, and to produce a histogram with a normal curve for each program. And there are ODS graphics available. General information for enabling ODS graphics is in Chapter 19. The default setting for SAS is that ODS graphics are enabled, and so that if they are not, please see Chapter 19. So I have here proc univariate CI basic. We were looking for 99% confidence intervals, and so that CI basic will generate confidence intervals for us. Proc univariate will generate 95% confidence intervals by default. So if we want something other than 95% confidence intervals, we need to specify alpha here at 0.01, and then finally request a test for normality with this normal option. We have a class statement. The class statement, we identify the group or the character variable program here, so it's going to compute the summary statistics that we saw in the default information plus these requests we've made here. It's going to compute that for each of the programs for the numeric variable score. Additionally, it's going to draw a histogram for the score variable and draw in a normal curve. This is Objective 3.2. So we highlight those statements in the run statement. We can see the addition here of univariate Objective 3.2. Okay. We scroll up. Objective 3.2, program equals A. The one just above is the combination of programs A and B together. They're not separated out. Now, back up here a bit. Notice when we want to use class program, this does not require that the data be sorted. And so that if we don't want to sort the data, the class statement is a good option here. The results, then it gives us that same delimiter as we saw before. We have program A, the univariate procedure for the score response variable. And so we have 14 observations in program A. Recall there were 30 altogether, so that must mean the other 16 are in program B. The basic statistical measures we saw before. So this moments table, basic statistical measures are the default information. The CI basic option generated this basic confidence limits assuming normality. So in those table 3.1 and 3.2, those confidence intervals were based on normality. It asked me for the 99% confidence interval for the mean. This is the y bar value for the mean. This is the confidence interval formed using that mean as the center. So that means we're 99% confident that the true population mean is between 68.6 and 83.78. Likewise, we have confidence intervals for standard deviation and variance. Table 3.2 gave us a confidence interval for the variance, which is what's computed here. The square root of each of those endpoints is what forms the confidence interval for standard deviation. So basic confidence intervals, then we must request if we want that to be a part of this output. We still have our test for location. We'll look at modifying this in Objective 3.3. New information is test for normality, and so we have 4 different test statistics listed here. So the statistic and the p-value. So we didn't go into the details associated with each of those test statistics like I did with the t-test, but at a glance here we can see that all of our p-values or observed significance levels are in excess of our and alpha, which would conduct the test here. And so given that we did 99% confidence intervals, we're making all of our judgments using alpha equals 0.01. Nothing here is close to being rejected, meaning that the data is very symmetrically distributed, and so we don't have any reason to believe that the data are non-normal in the population. You still have quantiles here for those selected percentiles listed. And the extreme observations then are listed here also. So we have the 5 lowest, the 5 extreme, and we only have a sample of size 14, so that means it's only 4 observations aren't included there. Then it gets repetitive in this same format, different data, because now the data are associated with program B. And so it repeats all these summaries then for the 16 observations that we had in program B. So we get confidence intervals and tests for normality, the same as we had for program A. The histograms, it put them together here. Over here at the left, program equals A, program equals B, and so that we're superimposing a normal curve on these. And so when we have small data sets, it would be very difficult to determine if the data are non-normal. The normal option on the histogram statement also generates this information, so we get a little bit of repetition here for tests for normality. The Kolmogorov, Smirnov, Kramir von Mises, and the Anderson-Darling tests are repeated. The Shapiro-Wilk test does not appear here again as it did before. So the second set of tests for normality that we get right here are from the histogram statement. So you can do either one or both. I did both of those here. And then quantiles here, a little different list than we saw given as the default information from the univariate procedure. Those tests are repeated then for program B, the first set being from program A. Because of that repetition in the normal tests, we could have just requested the test for normality on the proc univariate statement and not on the histogram statement, or we could have made the request on the histogram statement and not on the proc univariate statement. And then the third option, of course, that we did was we include the normal option on both of those statements, and so that we don't get as much repetition then if we specify it in only one place. Next, we'll demonstrate the output statement. So when we have a basic syntax, proc univariate, and a variable statement, we can use an output statement to create a data set. So this is different than data input data lines. The procedure can create a data set, and the data set can have summary statistics in it, but not the raw data. And so we can choose which statistics we want to output, so that's statistic 1 through statistic m, where m can be any number, and then the list on page 33 in chapter 3 begins with the things that we can output. So where it says statistic 1, you can put in things such as n miss, n obs, etc., down through the bottom of this list. Statistics variable 1, we can have multiple variables in a univariate procedure. In our example so far, all we've seen is one variable called score, and so therefore we would only have a single stat1 variable 1. We wouldn't have a long list such as demonstrated here. So we'll just do this for a very short list. We'll look at this in greater detail in future operations. Objective 3.3 illustrates how to use the output statement. We can look at it using both a class statement and a by statement if we wanted to. Alright, so we also want to show how we recover more information or a test of location. Suppose instead of population mean equals 0, such as the default, we were interested in whether or not the population mean for each program is equal to 75. So I have a class statement. I use mu0 equals 75. It's equal to, this is mu0, not mu-o. If I put an o in there instead, even if it's a capital O, it's slightly different shape. You'll notice the color change. mu0 is blue. That's the allowable syntax there. And so that we can specify again on our histogram a normal curve, and we can tell it, put that value of 75 at the mean of that distribution that you're going to draw. In our output statement, we're going to recover the mean, the sample size, and the standard error of the mean in a new data set called 3. Okay, so here we have 3 is the name of our new data set, the mean for score, the sample size for score, and the standard error of the mean for the variable score. So these choices here for the variables are my choices. I put score there. Suppose I would have had more than one variable listed in this VAR statement. I want the name of the variable to occur in there, so that way I know which one's which. And then the MN is kind of a shorthand for mean, N for sample size, and SEM is another way of representing a standard error for the mean. So you could name those anything you want, but they do have to be something, the names do have to differ from each other is the thing you should remember. Okay, and so that here proc print data set equals 3, so we'll output those here. Okay, so first our objective 3.3, we have here moments for program A. Started out, so that part's the same. What's different now is this test for location, mu0 equals 75. Now I have a t-statistic of 0.48 and a p-value 0.63, so the population mean for program A is not different than 75. We see the same quantiles and extreme observations information that we saw previously in the default. Then we look at program B, same moments and basic statistical measures. Test for location is different. Notice also different from objective 3.2, I don't have the confidence intervals requested here, so that's why I don't have that table of confidence intervals produced. Now in this instance, in program B, I do have a t-statistic of 4.196 with a p-value of 0.0008. If we're operating at the 0.01 level to draw our conclusions, as written in the statement of objective 3.3, here we would find that the mean of population B does differ from 75 because that p-value is less than alpha. Then we have our histograms, and we asked for 75 to be drawn in as the mean, and so we can see the data in program B are shifted to the right of that 75, and so therefore that's what we're picking up in that second t-test. And it gives us the information then that tests for normality on each one of our programs. Then lastly, we asked for it to print the output data set, and so for the class statement it gives me the results for program A and program B and tells me then the sample size, the mean, and the standard error of the mean. Those are the things that I requested. So I could have put a VAR statement on this proc print statement, but I did not. It gave me them to me in a little different order than I made the request here. Okay, but that I have all of those. If I want those reordered, then I can use a VAR statement on the print procedure. Though our data set is limited in only one numeric variable here, if I would have had several variables, score, and let's just generically call it variable B, variable C, this mu0 equals 75, it would test whether all of those variables have a mean of 75. If you check your book, you'll find some alternate syntaxes for when you have multiple variables in the VAR statement, and how do you specify the different values in mu0 if you want the test of hypotheses done for each one of those variables. And so that information is given to you in Chapter 3. Specifically, the syntax for those options is given on page 44 in the textbook. And so you can see then the different syntaxes allowed for when you have multiple variables here. Additionally, I want to point out that when you draw the histogram for your particular variable, you can use the value of the mean in the data set or specify a mean here. You can also specify the value for sigma that determines the shape of the normal distribution. So any of those hypothesized values can be specified for the graphic. Otherwise, it just uses the value of the sample statistics, that is the value of y bar and the s, the standard deviation. Now, if we wanted to do this using a by statement here instead, you could do this by program, but prior to this you would have to be sure to sort the data instruction. You'd want to sort it by program to make certain things are in order. So that means then that this by statement is compatible with this by statement. It doesn't matter if it's ascending or descending, just so long as they're compatible statements. So if we change this to a by statement, excuse me, and then run this and look at a print of this. So this is kind of our kind of a part 2, if you will. Sort the data set, make sure we capture that, and then run. So notice each procedure has a run statement, except for the sort. It's only necessary that the last procedure has one and that you pick it up when you highlight things such as I've done. Of course, I could have just clicked the little running man for the whole program, but it would repeat objectives 3.1 and 3.2. Okay, and so that if we look at these, we get a little different appearance here, program A, program B, that we didn't see. We do see that when we use it up here on the class. In this particular instance for this procedure, it doesn't look like it's done any differently, I think, than we saw before. So that works all right, and when we do the proc print on the data set, we get the same information as we've seen before. So one of the cautionary notes here is sometimes when a class statement is available and a by statement is available, they may not always do the same thing, and so we want to be attentive to that, and we'll demonstrate that in the proc means procedure that's in the second part of Chapter 3.